Okay, we should get started. So before we start, any questions about the previous lectures and homeworks or exams? Possibly this weekend. Most likely. Okay. Okay, no question. Great. So yeah, before we start, I just want to clarify this equation, right? So this is our integral mass balance equation. We have to use it in our homework and in our exams. So there's some confusion regarding the nomenclature here. So there are two S, if you notice here, right? But they have different meanings, right? This S refers to the surface of the control volume, right? The surface enclosing the control volume. This SI here refers to the reaction rate or the production rate of species I in the control volume. Okay, so they are just two different parameters. So sorry for the confusion. Okay, yes.
I have on problem 3, part 2. You ask for moles of A, but then you give the symbol for molar flux. Which one do you want?
Sorry, can you say that again?
Yeah, so homework 2, problem 3, part 2. You ask for the moles of A, then you give the symbol for show a graph for molar flux. So which one do you want?
Oh, okay. So either molar flux or moles of A.
Yeah.
Okay. I need to look into the problem. Yeah, because I don't remember. I'll send an announcement later about that. Okay. So today we're gonna continue to talk about mass transfer coefficient. So in our last lecture, I think I was going too fast, so maybe that was not easy for you to take in. So I'm gonna go over or review some of the key concepts again. So just to make sure you can understand. Okay. So we talk about there are three mechanisms for mass transfer, right? There's bulk flow, in which as long as we have a bulk motion of the fluid, then this bulk motion of the fluid will carry all the chemical species in this fluid, and that will create a mass transfer. And the second mechanism is called molecular diffusion. This will happen whenever you have a concentration gradient, because we know molecules are doing random walk at the molecular level. So even though at the molecular level, this motion of the molecule is random, but at continuum level, when you have tons of molecules, and then this movement becomes connectively, they have a direction. And if you have a concentration gradient, then basically the molecular diffusion will tend to mitigate or smooth the concentration gradient. Okay, and this is called molecular diffusion, and it's kind of the slow process. It can be mathematically computed using the Fick's law. So the third mechanism is called turbulent or eddy diffusion. This happens in a turbulent flow when we have eddies. Okay, so when we have a turbulent flow, if you look at this schematic, this example, right, you could have flow in this direction, right? That's kind of the direction that is parallel to the plate or to the wall. So, and that's the mass transfer due to bulk flow. But meanwhile, in the direction that is perpendicular, right? If we look at this is x direction, if this is z direction, if we look at the direction that's perpendicular to the surface or to the wall, because the wall is impenetrable, so there's no normal direction velocity, even though you have eddies, right? which means if there's no normal direction velocity, then there's no bulk flow in the normal direction, right? Because the flow won't penetrate the wall. So there's no bulk flow perpendicular to your wall. But because of the eddies, they are doing this motion, and they will mix chemical species in the fluid. So that will create a mass flux in the z direction, right? And this is called eddy diffusion. And it's called eddy diffusion. I mean, although fundamentally it's still a mass transfer caused by the fluid motion, but it's called eddy diffusion because empirically it behaves similar to molecular diffusion. Or another way, historically people try to apply an equation that's similar to Fick's law to describe the mass transfer due to eddy diffusion, right? That's why it's called eddy diffusion. So we'll talk about this more later. So these mass transfer mechanisms, they are additive, which means that you can add them together. And we've learned that the total molar flux can be broken down into two parts: the convective flux, right? That is basically proportional to the molar average velocity of your fluid multiplied by the concentration of species A, if you are computing the total mole flux of species A. Okay, then plus the second component is a diffusive molar flux. Okay, and in our previous lectures we talk about only molecular diffusive flux due to molecular diffusion, and we have shown that for the diffusive flux due to molecular diffusion, it can be computed using the Fick's law, right? But now eddy diffusion is something different. So depending on the fluid flow condition, right, you could have 1, 2, or even 3 mass transfer mechanisms, right? And also you should, when you look at your problems, you should be aware that the mass transfer in different directions could be different, right? So always when you look at one mass transfer mechanisms, you need to be aware that what direction you are talking about. For a stagnant medium, when there's no flow, there's no bulk flow, then there's no convective flux. Since there's no flow, then there's no eddies, right? So you will only have molecular diffusion. If there's a laminar flow, right, like we just showed, right? So you have flow happening in this direction. Then for sure you will have mass transfer due to bulk flow in the x direction. And whether or not you will have molecular diffusion depends on if you have concentration gradient, right? So if you have concentration gradient in the x direction, then you will still have molecular diffusion in the x direction. But in the z direction, that's perpendicular to the surface. This is the wall. Then obviously there's no bulk flow. So in this case, the only possible mass transfer mechanism is molecular diffusion if there's a concentration gradient in the z direction, right? If there's no concentration gradient in the z direction, then you don't even have molecular diffusion. So, and if you have a turbulent flow, then you will have eddies doing this motion. These eddies may move together with the fluid in the x direction again. So you will have bulk flow in the x direction if you have that bulk flow. And in the z direction, again, if you have concentration gradient in the z direction, you will have molecular diffusion, right? And now because you have eddies, and eddies are doing this motion, they will create mixing locally that will create z direction mass transfer that is faster than the molecular diffusion. So for bulk flow, the convective molar flux can be computed if we know the concentration of the species as well as the velocity of the bulk flow, right? And for diffusive flux for due to molecular diffusion, right? We can compute the flux if we know the diffusivity and we know the concentration gradient. So we can, there's a theory in which we can write down an explicit equation to compute the flux, right? For bulk flow, for flux due to a bulk flow and molecular diffusion. But for eddy diffusion, there's no like fundamental theory to compute its flux because it's so complex. And so then historically, we developed some empirical correlations just to based on experimental observations to make some approximations. So we developed some approximated way of computing mass transfer flux due to eddy diffusion. And that's the theory of mass transfer coefficient, right? So it's an empirical method for us to solve mass transfer problems based on experimental observation. And second, it can be applied to solve not only diffusive flux due to eddy diffusion. It can also be applied to solve diffusive flux due to molecular diffusion or even convective flux. Okay, under certain assumptions. So next, I'm going to show you the examples. So the first example is kind of the simplest example where we have only molecular diffusion, right? So if we have a membrane and across the membrane, there's a concentration difference of species A, then there's such a driving force to create molecular diffusive flux from molecular diffusion. Now we know in this case, we can apply Fick's law to compute the diffusive flux, right? As long as we know the concentration, we know the diffusivity, and we know the gradient, right? In this case, we're considering a 1D scenario, and for the gradient, as long as we know XA, the mole fraction of A as a function of Z, right? It's kind of the concentration and the mole fraction of A in the direction of Z, then we can compute its derivative dxa over dz, right? Then if we plug that back into this equation, we can compute the diffusive flux. But now it's not always possible we can get the mole fraction or concentration of our interested species in the, as a function of the spatial coordinate. Or in some cases, we can solve for it, but it just takes too much effort, which is not worth it, right? Then in this case, we can approximate the derivative, right? So this is the derivative of dxa over dz with the ratio of difference, right? We can approximate. So in here, we can approximate this derivative with the difference of mole fraction of A divided by the across the membrane thickness divided by the membrane thickness, right? This is an approximation, and for sure, if XA is a linear function of Z, right? Then in this case, they are equal. The derivative is equal to the ratio of the difference, right? That's the only case this can be exact, but for other scenarios, it's only an approximation. Okay, then if we plug in this equation back here, we can get we can get an equation in which we can compute the molar flux due to molecular diffusion with only the diffusivity, the concentration, the difference in the molar fraction, and the length or the thickness of the membrane. Okay. Now, if we define Sherwood number to be a ratio, right? This is a ratio of the this is a ratio of the mass transfer coefficient divided by this. Okay. This is ratio of mass transfer coefficient and DAB over L. If we define this to be Sherwood number, And then if Shelf number is 1, that means Kc equals DAB divided by L, right? Then we can just plug in this back here, right? Just replace DAB over L by Kc. And meanwhile, you can plug in C into this, right? Then we can get the molar flux due to molecular diffusion by this by this equation, in which it's basically we are multiplying the mass transfer coefficient with the concentration difference across the membrane, right? Now the problem is simplified to the problem is simplified to the degree that as long as we know the mass transfer coefficient, then we can compute the molar flux due to the molecular diffusion. Okay. So in this case, the mass transfer coefficient, it has a unit of length over time, right? Because if you look at this equation, Kc is basically, in terms of unit, it's basically Ja over concentration, right? And we know that the flux has a unit of mole per meter square per second. Then we have concentration has a unit of mole per meter square, meter cube, right? And if you further, simplify this, you will get this to be meter per second, right? So that's why mass transfer coefficient will have the unit of length over time. And this is similar, this equation is analogous to the heat transfer equation. And this is useful if we don't know, or if we don't want to know the mole fraction Xa as a function of Z. And basically how well we can compute the flux, it really depends on how good the mass transfer coefficient we get. Okay, so in this case, we made the assumption that the Sherwood number is 1, so we can just draw a equal sign here. But in reality, the Sherwood number equals 1 is kind of very rarely satisfied. So so we cannot, this is like a very strong assumption that is kind of really useful. In practice, there are like 2 ways we can get mass transfer coefficient. One way is we can still solve for Xa as a function of Z, right? Now then you can go back to the mass, right? So if you know Xa as a function of Z, you can get the exact value of this Ja, right? Because now you can just apply Fick's law, right? And you can compute Ja. Now the difference in concentration gradient. Then Kc is just, in this case, Kc is just can be computed by dividing the Ja by the Ca1 minus Ca2, right? But that's the case, exactly what is the functional form of Xa as a function of Z, which a lot of times is something we don't want to do, or we want to avoid. So then we have to, resort to the second method, in which is to basically find out what is a Sherwood number, right? What is the real Sherwood number? If it's not 1, then what it is? From a lot of experimental observation, people found that Sherwood number is correlated with non-dimensional groups like Reynolds number, Schmidt number, and Packnet number. Okay, so next, I'm just going to introduce 3 example systems in which we can find Sherwood number, and depending on the and correlate the Sherwood number with the fluid flow condition. So the first example is falling laminar liquid film, in which we have a liquid film of thickness of delta that is falling from a wall, right? That's falling from the wall. And from fluid mechanics, you can solve for the velocity of the fluid in the velocity in the y direction. Well, in the z direction, there's no flow, right? because the wall is impenetrable. But in the y direction, because of the gravity is pulling down the liquid film, you can compute the velocity as a function of the location in the z direction, z, right? So again, this is a parabolic function. At the wall, the velocity is 0, and at the kind of the surface of your liquid film, you have the maximum fluid velocity. Okay, and meanwhile, if there's a if we have a gas phase A here, and this gas phase A will dissolve into this liquid film B. Right, let's see if this is B. A is gas, it will dissolve into the liquid film B, right? Then we know there will be concentration gradient of species A in the Z direction, right? Because apparently there will be higher concentration of A at the surface than at the bottom of the of the liquid film, right? So then in the Z direction, then in the Z direction, there's no flow. But because there's such a concentration gradient, we will have a mass transfer of A due to molecular diffusion, right? So in this case, obviously we can always solve for the mass transfer flux of species A using Fick's law, so long as we know that the concentration of A as a function of Z, right? But if we don't want to know C as a function of Z, if we just don't know it, that's where we can apply the mass transfer coefficient equation, right? And we can know, and we should be able to know the concentration. If we know the concentration difference between the surface and at the wall, then as long as we know the mass transfer coefficient, we can solve for the mass transfer flux. Okay. So in this problem, the Scherl number, right? That's the ratio of the mass transfer coefficient over diffusivity diffusivity divided by the characteristic length L, right? Is correlated with eta, which is defined by this equation, in which we have the film thickness, the characteristic length scale, and the Pachner number, momentum for mass transfer. So the Pachner number for a mass transfer is the product of Reynolds number and Schmidt number. Okay, and Schmidt number, NSA, is the ratio between momentum diffusivity, right? Which is mu divided by rho, and mass diffusivity, DAB. Right. So then, from a lot of experiments, people have found that there's such a correlation here, as you can see. Depending on the condition, for short residence time solution, so you will have the Scherl number to be dependent on on the eta in this line. For long residence time solution, it's going to be this. It's going to be a constant. So the Scherl number will be a constant, which is about 3.14. Okay. So now if you get the Scherl number, then from this, given this problem, then you can compute the the Schmidt number. You can compute the Reynolds number. That will give you the Pachner number, right? And if you plug in the Pachner number into this equation, that will tell you where your system is on this figure, right? For example, if you plug in all the numbers, you find out eta is here. Then if you go up, you'll find out your Scherl number is at this point, right? Which is at this point. With the Scherl number, you can compute Kc is equals to the Scherl number multiplied by DAB divided by L, right? Now you have mass transfer coefficient. Then you can plug in the mass transfer coefficient into your equation and compute your mass transfer flux due to the molecular diffusion. Okay, that's for a falling laminar liquid film. So the second scenario is a fluid flowing across a flat plate, right? In this case, we know when the fluid flowing across a flat plate, then it will develop a velocity boundary layer, right? Outside the boundary layer, the fluid velocity will be, the initial velocity when it just, encounters this flat plane. But in the velocity boundary layer, your velocity will be dependent on this distance from the flat plate, right? With this equation. So the x direction, which is this, again, this direction, x direction velocity is dependent on the z coordinate, which is basically the distance of your from the flat plate. Okay, then we can define delta over x. Delta is basically the thickness of your velocity boundary layer. X is basically the distance. X is the distance of your flow from the initial point where your flow encounters the flat plate. Okay, and this is dependent on the Reynolds number. Okay, now in this case, the Sherwood number is going to be dependent on the, it can be, computed by this equation, in which it's dependent on the Reynolds number and this is Schmidt's number. Okay, so again, for this type of problems, and you can first compute Reynolds number and Schmidt number, then you can plug in the Reynolds number and the Schmidt number into this equation. You can compute the Sherwood number. Then you should be able to compute the mass transfer coefficient. Then you can use the mass transfer coefficient to compute the mass transfer, the flux due to the molecular diffusion. So the third example is flowing fluid in a circular tube, right? In this case, it's similar to the flow across a flat plate, but in this case, you have you have a circular tube, right? You have a circular wall. So your velocity, your velocity boundary layer will increase until some point. It's just gonna expand to the whole cross-sectional area of your tube. In this case, you will have a fully developed tube flow, in which the velocity in the x direction is going to be a parabolic function of your radial direction coordinate, right? So we know this. So in this case, the Sherwood number is basically dependent on the mass transfer Packnet number. Okay, by this equation again, similar, and it can be plotted into this kind of like into this figure. So you find out the Packnet number, the x and d. Then you plug in, you go to this figure and you find out the Sherwood number. Then you can compute the mass transfer coefficient, and you can compute the mass transfer flux due to the molecular diffusion. Okay, so that's like 3 examples in which we can apply mass transfer coefficient to solve for mass transfer flux using due to molecular diffusion, right? And the kind of the key here is really to find out mass transfer coefficient. In a lot of cases, you need to find the Sherwood number, which depends on the specific geometry of your flow condition, as well as the Reynolds number, Packlet number, and this like dimensionless number that describes your flow. Now let's look at the second example in which we can apply mass transfer coefficient to solve for the mass flux when we have both convective and a molecular diffusive flux. So in this case, we start from the total molar flux equation, right? That consists of the convective flux due to bulk motion plus the diffusive flux. And the convective molar flux for a binary system is made of the so here N is the total convective flux. For a binary system, it's made of the molar flux, total molar flux of A and B, right, due to bulk flow. So we know in certain examples, right, this equation can be further simplified, right? That includes evaporation, condensation, adsorption, stripping, and the property of these examples, the uniqueness of these examples is that, for example, let's take the evaporation as an example. Here we have the liquid benzene, which is our species A, that is evaporating from the beaker into the air, which is our species B. So we have a binary system. Then in this case, so we have the flux of A going in this direction, and we have flux of B going in this direction. And at a steady state, we know that when liquid benzene is saturated with air, then the molar flux of B downward will be negligible, right? So in that case, in other words, MB is much smaller than MA. Okay, so for this type of problem, we can further simplify this equation here, right? Basically, if we drop, because MB is much smaller than NA, if we drop out MB, then we'll have NA on both sides of this equation, right? If you do some rearrangement, move XA NA to the left, that will give you 1 minus XA bracket multiplied by NA. Then you can just move 1 minus XA to the right. So you have the total molar flux to be dependent on the diffusive molecular diffusive flux divided by 1 minus XA, right? Then we know for the diffusive flux, the Fick's law can be approximated by using the mass transfer coefficient Kc multiplied by the concentration difference, right? Then you just plug in this equation back there. So you will have this, right? So basically just plug in this, replace the JA replace JA with that, you get this equation. And now if we define Kc prime as Kc divided by 1 minus XA, this is like a modified mass transfer coefficient. And then we can change this equation to a similar functional functional form that's just similar to the previous equation in which we solve the diffusive for the diffusive flux using mass transfer coefficient. Yes.
Does this apply to all of those examples, or is this just evaporation that we're talking about?
So it is applicable to the case whenever you have, first of all, it's a binary system. Second of all, your flux of one component is much smaller than the flux of the other component.
Okay.
So, and evaporation is one example, it's applicable. And there are other examples, right? Like these 3 examples, they are also applicable. But as long as your flux of one component is much smaller than the flux of other component, this equation is applicable, right? Now, finally, we can look at the mass transfer in turbulent flow. So in this case, because turbulent flow will have eddies, and it's most common because in the chemical industry, because eddy diffusion leads to faster mass and heat transfer, that will lead to smaller equipment, which is desirable. But we talk about there's no fundamental theory to describe eddy diffusion. So in turbulent flow, so there's no streamline. There's mixing due to eddies because there are velocity fluctuation in the eddies. And what is of interest is the normal direction mass transfer due to eddies, and that's called eddy diffusion. That is much faster than the molecular diffusion. So in this specific example, there's no bulk flow in the z direction, right? So this is the x direction. If this is the z direction, since there's no bulk flow in the z direction, now we can write down the z direction total molar flux to be composed of only diffusive flux, right? And for molecular diffusion, we know that diffusive flux, can be computed by the diffusivity multiplied by the concentration gradient. Now, with eddy diffusion, so it behaves similar to molecular diffusion, because when eddies moves, it's like, because we know that the molecular diffusion is due to the random motion of molecules. The eddy diffusion is like, eddies are also doing sort of random motion that will create mixing and mass transfer. So that's why eddy diffusion is kind of somewhat similar to molecular diffusion, right? So that's why we can apply the similar functional form to compute eddy diffusion, right? So long as we add an additional parameter that's called eddy diffusion diffusivity into this equation, right? Just to modify the Fick's law. And similarly, we can apply the similar equation to heat transfer and momentum transfer. So in heat transfer, we have temperature gradient as a driving force, we have heat conductivity, and we have the eddy diffusivity for heat transfer. And then similarly, we have the momentum transfer. Now, if we look at this problem, we find there's kind of some inherent similarities between the mass, heat, and momentum transfer. And that just, gave us some hint that if we can find the inherent correlation, maybe we don't have to solve for every problem. We don't have to solve we don't have to solve every problem, right? If we can solve for momentum transfer, maybe you can solve for mass transfer and heat transfer. So that's kind of the idea. People study analogies between these three diffusive flux. So we have diffusive mass flux. Again here, NA is refers to the diffusive mass flux here because there's no z component velocity, right? It can be described by this modified Fick's law functional form. And now if we introduce mass transfer coefficient, right, then it can be computed by multiply the mass transfer coefficient with the concentration difference. Similarly, we can do the same for diffusive heat flux and diffusive momentum flux. Okay. Now, this is when we basically connect this functional form with the mass transfer coefficient, heat transfer coefficient, and the Fenning frictional coefficient. There's no way we can find the eddy diffusivity, so that's why we want to find out the mass transfer coefficient, so we can apply this equation to compute the flux. Okay, and we talked about this in our last lecture. If you do some non-dimensionless analysis, right, by scaling your velocity, temperature, and concentration with a corresponding reference point, then you can convert the derivative here, this three derivative, into a similar functional form, right? That is at z equals 0, the d theta dz for mass transfer, it's the ratio of mass transfer coefficient divided by the total mass transfer diffusivity, right? And this is similar. We can do the same for heat transfer and momentum transfer. We get this functional form. Now, how do we leverage this functional form to find out mass transfer coefficient? So if we do some further assumption here, if we assume momentum diffusivity is the same as thermal diffusivity, that is to say the Pareto number is 1. If we assume the momentum diffusivity is the same as mass diffusivity, that is to say the Schmidt number is 1. And further, if we assume all eddy diffusivities are equal, right? That's to say epsilon D equals epsilon H equals epsilon M. Now what we find out is this term is equals to this term equals to this term. So that we can just eliminate these 3 terms in this in this equation here. So that gives us the so-called Reynolds analogy, right? So if you just drop out the diffusivity terms, you will have the F/2. So then you move velocity over to the right side of your equation. Then you will have F/2, that's from this equation, equals H over rho CpUx, that's from this, equals this, okay? So in this way, if you know so this is the heat transfer Schmidt number, and this is the mass transfer Schmidt number, right? In this case, as long as you know the thinning frictional factor, then you will be able to compute the mass transfer coefficient, right? If you know F, then you can compute, and if you know Ux, you can compute at Kc. Then you can use Kc to compute your mass transfer flux. Now this equation has very limited practical use because as we see here, in order to get the Reynolds analogy, you need to make several assumptions, including the mass transfer, thermal, and the momentum diffusivity need to be equal. This is a very strong assumption. So next, we're going to talk about the other analogy that's called Chilton-Coben analogy. That's more practical. Okay. Questions?
Do we ever actually use Reynolds analogy to make the full problem stuff?
So as long as your system satisfies these assumptions, right? Where you have your momentum diffusivity equals to your thermal diffusivity equals to your mass diffusivity, and your eddy diffusivities are equal, then you can apply Reynolds analogy.
What, like, in reality though, what application when could we say that that's true?
Very rare. So that's why, it's conceptually, it's a good starting point for us to really, use the analogies between this heat, mass, and momentum transfer to derive such an equation that help us to connect the thinning frictional factor with mass transfer and heat transfer coefficient, right? Conceptually, it's helpful for us to sort out this problem, but practically, it's not that very useful, but at least it's a good starting point to tell us, this analogy analysis is useful,
Okay.
right? We just need to kind of like modify it, make it better, right?
Okay.
That's good.